All right, let's try one from our fluid chapter here. Number 30. It says this: convert normal blood pressure of a 120 millimeters of mercury over 80 millimeters of mercury into newtons per square meter using the relationship of pressure due to a fluid height rather than the conversion factor. So we have a conversion factor that converts millimeters of mercury to pascals or newtons per square meter. But they just want us to kind of use the fundamental idea of rho GH. All right, so if we have mercury that's 120 millimeters high, I'll start off with the density, which is 13,600 kilograms per cubic meter. G is 9.8 meters per second squared. And then the height is this 120, and I'll put here millimeters and of mercury. And so if you look here at the units, you'll see that right here you get a kilogram meter per second squared. That's a newton. And then this meter in top would cancel with 1 down here, and so you're going to get newtons per square meter, which is your Pascal. So 13,600 for the density, 9.8, and then 120 times 10 to the negative 3 comes out to be 15,994 pascals. And so that's our conversion factor. Or, excuse me, I guess that's not a conversion factor. That would be the pressure of 120. By the way, then if I divide that by 120, so I find out what it is per 1 millimeter of mercury, that's our conversion factor. So that's what they're saying. You didn't want you to do the problem, but you could have done what is it for 1 millimeter and then multiply by 120. But that's the 133 was our conversion factor. Now, the lower pressure is the same basic idea, except we would have a smaller height of 80. So let me just go back in my calculator to this last entered formula and change this to an 80 and hit enter. And so this must be 10,662 pascals. And by the way, pascals are pretty small, so a lot of times our gauges would read, I'll round it up to 16.0 kilopascals. And so we'd have a little gauge that say 16 kilopascals. And this one here would read 10.7 kilopascals. Now, part B says, discuss why the blood pressure in an infant would be much smaller than adult. And of course, hopefully you kind of see the size that, if you have a full-grown adult, and now they even said infant. I'll just do a toddler, so they're standing up, and maybe infant, they're lying down if they can't quite sit up or walk yet. Yeah, the point is, the heart doesn't have to be able to go uphill by very much, and it doesn't have to flow much distance. Now, this chapter is a little early for talking about the loss of pressure due to viscosity. That's in the fluid dynamics coming in the next chapter. But for both reasons, the fact that an adult is higher up and travels then through shorter distance of piping, there's less effects of viscosity and less effect of height. So either way, when you put both of those together, an adult doesn't need, and also, well, as part of the viscosity, you'll see it has to do with volume flow. So not only is it the distance, but it is the volume. For all those reasons, the adult needs a bigger blood pressure and a higher blood pressure. So I think they just wanted to mention height in this one. That was kind of the thinking behind this chapter. All right. That one's good.